stato ospite del centro liceo interdisciplinare di scienze matematiche e loro applicazione alcuni anni or sono, tenendo una brillantissima conferenza di carattere autobiografico relativa alla meccanica quantistica, nella quale egli è stato uno dei protagonisti. La relativa conferenza è stata pubblicata ed è una delle prime pubblicazioni della nuova collezione dell'Accademia dei Lincei relativa appunto ai contributi del centro liceo. L'iniziativa odierna ha un carattere un po' diverso, pur essendo ancora nella stessa linea storica e, diciamo così, anche personale di quella conferenza. L'argomento è la storia del positrone, ed è inutile che io ricordi che il positrone è stato scoperto attraverso sviluppi matematici precisamente dallo stesso Dirac. Aggiungerò soltanto che queste scoperte così richiamate sono state l'avvio degli sviluppi più importanti della fisica attuale, riguardanti la fisica delle particelle elementari e lo studio dell'antimateria. Detto questo, è inutile che io mi sovrapponga a quanto ci esporrà tra poco il conferenziere e darò soltanto la parola al professor Tušek per ricordare, affinché egli ricordi il tipo di questa iniziativa che sta proseguendo, che ci ha avuto due precedenti con le conferenze tenute alcune settimane or sono dal professor Tušek e la settimana scorsa dal professor Amaldi. Credo dove Tušek se vuole.
Well, I've very little to add to this, and I've just to apologize to Professor Dirac for the lights, which might be terribly blinding, and to point out, that this thing, which he can watch and where he can see what he's doing, is an anti-mirror, which should not be too difficult for Professor Dirac to interpret. And of course the wrong way around. This is the only occasion where you see yourself not in a mirror, but in a double mirror, and that has to be learned. I'm very, very pleased to see Professor Dirac here, and he'll enjoy it as well as you.
The story of the positron is a story of a physical discovery that was made by theoretical arguments. Now, you may wonder in the first place, how is it possible to make a physical discovery just by theoretical arguments? It's easy enough to understand how an experimental physicist can make a discovery. He works with his apparatus, gets some new unexpected results, and finds an interpretation for them. But the theoretical physicist is just sitting in an armchair and thinking things over. How can he be led to a discovery? The answer is that he works from the mathematics. He takes the mathematics of the existing theory. There is a formalism, a number of equations which have to be interpreted in a certain way. He studies this formalism and notices an imperfection in it. And then he proceeds to try to remove this imperfection. If he succeeds in doing so, he will be led to some new equations. Then he looks for the physical meaning of these new equations. The thing that I want to emphasize is that the mathematical development comes first. The physical development just follows along behind the mathematics. There is a good example of this procedure provided by Maxwell's discovery of the equations of the electromagnetic field in the last century. Maxwell examined the equations of the electric field and the magnetic field which people were using at that time, and he noticed that they are not consistent. Now, if your equations are not consistent, that is a very serious defect, about the most serious defect you can have. It is imperative to do something about it. Now, Maxwell found that these equations could be made consistent if one brought in another term. With this new term, one had some new physical phenomena appearing. In particular, one had the possibility of electromagnetic waves. In that way, Maxwell was led to the prediction of electromagnetic waves, which was subsequently very brilliantly confirmed by experiment. The story of the positron is similar in its general outline. One starts from certain equations that have a fault in them, and one tries to improve on them. The equations that one starts with are the standard equations of quantum mechanics. I must tell you a little about these equations in order that you may appreciate the argument. I shan't go into the mathematics more than is necessary to bring out the important features for the story of the positron. Quantum mechanics was discovered by Heisenberg in 1925. He brought out a new system of equations. At first, they were very imperfectly understood, but it needed only a few months before people understood these equations pretty well. The main feature of these equations was that they used dynamical variables which do not satisfy the commutative law of multiplication. If you have two variables, u and v, and you multiply u by v, the result is not the same as if you multiply v by u. This was very surprising, and I remember very well the great effort of imagination needed in order to learn to work with these new variables. But it soon turned out that these new variables are really very close to the old variables that one used with the Newtonian mechanics. The old mechanics, which one calls classical mechanics to distinguish it from the new quantum mechanics, becomes most closely parallel to the new mechanics when one expresses it in the Hamiltonian form. That means that one works with certain dynamical coordinates, which we call q's, and some momenta conjugate to them, which are called p's. Now, in classical mechanics, all the dynamical variables commute with one another. The order in which one multiplies two of them together does not matter. In quantum mechanics, one has to replace these assumptions about the variables all commuting with one another by the assumptions which I have written down here on the board. The q's all commute with each other. The p's also commute with each other. But if you take one q and one p, they may not commute with each other. They do not commute if they both refer to the same degree of freedom. We have QR PS minus PS QR. equals I, the root of minus 1. This cost h, which is a universal constant, Planck's constant divided by 2 pi, and this delta rs, which means 1 when r equals s, and 0 when r is not equal to s. We have these commutation relations lying at the basis of quantum mechanics. We assume these equations, and then we have a formalism which is very similar to the classical Hamiltonian dynamics. In fact, if we take any two dynamical variables, u and v, and uv minus vu becomes equal to IH times a quantity which we may write as a bracket expression, uv like that. And this bracket expression just corresponds to the classical Poisson bracket. Now this is pretty abstract, what I've told you here, but it has the effect that one can immediately write down equations of motion in quantum mechanics. The equations of motion of classical mechanics are like this. Any dynamical variable u satisfies the equation du by dt equals the Poisson bracket of u with this quantity h, which is the total energy expressed in terms of the q's and the p's. It's called the Hamiltonian. Now, if we interpret this bracket expression according to this formalism, we get IH du by dt equals u capital H minus capital H times u. There you see we have equations of motion which we can apply whenever we know that Hamiltonian operator. You see we have quite a powerful formalism whenever we have a classical dynamical system and can describe the equations of motion in the Hamiltonian form. We can set up the corresponding equations of motion in quantum mechanics. It was really very satisfactory to have this general method of passing from classical mechanics to quantum mechanics. But one soon saw that quantum mechanics is really more general and powerful than this. You may take dynamical variables which are not expressible in terms of q's and p's according to this scheme of relations between the q's and the p's. We may have any dynamical variables consisting of any dynamical variables defined by our being given the commutation relations between them. They might be just the operators of some group, for instance. And with these more general dynamical variables, we can still set up a Hamiltonian as a function of these more general dynamical variables, and we can write down the equations of motion for this Hamiltonian. The more general dynamical variables might be the spin variables of some particle, or they might be variables referring to the emission or absorption of particles. We can bring in these more general variables and set up a quantum mechanics involving these more general dynamical variables, and we have a consistent scheme of equations of motion. Well, that is all very satisfactory as far as it goes, but it is not a complete physical theory because we don't know how to interpret these dynamical variables. The interpretation in classical mechanics is quite trivial. one gives numerical values to the variables entering into one's problem. But we cannot do that in the quantum theory. If u times v is not the same as v times u, we cannot say, for example, that u equals 3 and v equals 4, because 3 times 4 is certainly equal to, not equal to 4 times, is certainly equal to 4 times 3. We cannot immediately interpret the variables of quantum mechanics. The interpretation was built up gradually. People started with just very simple examples where they were able to guess at the interpretation, and proceeded to more general examples, and the general interpretation was worked out after about 2 years. The general interpretation of quantum mechanics is most easily expressed in terms of another formalism that was introduced by Schrödinger. Schrödinger was working independently of Heisenberg, but he set up a formalism which was soon found to be equivalent to the formalism of Heisenberg. He had wave functions and linear operators operating on the wave functions. Now, the linear operators of Schrödinger turned out to be just the same as the non-commuting quantities in the Heisenberg equations of motion. Schrödinger's theory added to the Heisenberg theory in providing a meaning for these operators, in providing a meaning for these non-commuting quantities. Namely, one can interpret them as operators operating on the wave function of Schrödinger. The wave function is usually called psi. And we may take psi to be a function of the variables q. The early form of the Schrödinger theory, psi was a function of the q's. And then each momentum variable, pr, is to be interpreted as minus IH and the partial differentiation with respect to QR. These operators satisfy just these commutation relations. And for that reason, the Schrödinger formalism is equivalent to the Heisenberg formalism. Now, the wave function psi is interpreted as referring to a physical state. And we can use the wave function to determine the probability of variables having specified values for that state. One forms mod psi squared, and one assumes that this gives the probability of the q's having specified values. Provided one suitably normalizes psi, that is to say, one multiplies it by a numerical coefficient, which has the effect of making the total mod psi squared for all values of the q's equal to 1. So then we have probabilities which add up to 1. The Schrödinger wave function satisfies this equation, IH d psi by dt equals capital H times psi, where this capital H is the same function as the H of the Heisenberg theory, and this capital H is now to be interpreted as involving the Q's and the P's, with the P's having the meaning of those differentiations. This equation of Schrödinger corresponds precisely to this equation of Heisenberg. We had there a general method for the interpretation of quantum mechanics. It was possible to transform this wave function of Schrödinger so as to involve other variables besides the q's. It might involve the momentum variables, or in fact any set of commuting variables. And the transformed Schrödinger function will give the probability of the transformed variables having specified values. This general interpretation for quantum mechanics, as I said, was worked out after about 2 years. Some people at any rate, did not like it very much because it involved talking about probabilities and not the certainties which we were used to in classical mechanics. This, however, is characteristic of quantum mechanics. In general, the calculations which we make in quantum mechanics only tell us the probability of certain variables having certain values. Some physicists have always objected to that probability interpretation, Einstein in particular, and Schrödinger himself did not like it. But still, after a lot of study and passage of several decades of time, this remains as the only general interpretation of quantum mechanics. One has to accept it because one cannot improve on it. Well, apart from this rather philosophical objection that we only have probabilities coming out from our theory, we have a very satisfactory formalism. Now, I want you to appreciate just ecosystems of classical mechanics, where we express all the variables in terms of q's and p's, but other dynamical systems involving different kinds of variables. The variables consisting of perhaps the operators of a group, or operators of emission and absorption, or any strange operators that one can think of which satisfy well-defined commutation relations. The formalism was extremely powerful and completely harmonious, self-consistent, and one felt very satisfied with it, except for one feature. There was just one objection to this formalism, namely, it did not agree with Einstein's special theory of relativity. This theory of relativity requires one to treat the time on the same footing as the three dimensions of space. Now, if you look at the equations of motion in either the Heisenberg form or the Schrödinger form, you see the variable t occurring in a prominent position. T, the time, is singled out, treated differently from the space coordinates. So the formalism is not a relativistic formalism. Suppose we apply the formalism to just a single particle. Then the q's will consist of just the three coordinates of that particle. We should then expect from relativity that those three coordinates should be treated on the same footing as the time. Up to a certain point, with the Schrödinger formalism, they are on the same footing because we have the three momentum variables connected with the three operators of differentiation of the three coordinates. And we have h, the energy, connected in a corresponding way with the operator of differentiation with respect to the time. However, when we look into it more closely and see just what h is, we see that there's no symmetry between the space coordinates and the time. This h is the energy of our system. If we just take a single particle by itself, that energy will be the kinetic energy of the particle. According to Newton, the energy of the particle would be 1 over 2n, v1 squared plus v2 squared plus v3 squared. This is the energy expressed in terms of the components of momentum. This form for the energy was used in Schrödinger's first papers. It gave fairly good approximation for the spectrum of hydrogen to which Schrödinger applied it. But it is a non-relativistic theory, and it can only hold for particles moving with small velocity. If we want to consider particles moving with the velocities comparable with the velocity of light, which we continually want to do in an atomic theory, we have to use the Einstein expression for the kinetic energy of the particle, which is c times the square root of m squared c squared plus p1 squared plus p2 squared plus p3 squared. This Einstein expression differs from the Newtonian expression, firstly, because it has an energy even with zero momentum, the rest energy of a particle, and secondly, because it involves the square root. Now, this square root is going to be very awkward if we insert this expression for the h in the Schrödinger equation. We have the square root of something containing operators of differentiation. We might try to give such a meaning to the square root if we have just a free particle in the absence of any electromagnetic field, by working with the momentum variables in the Schrödinger wave function. But in general, when there is an electromagnetic field present, it becomes very awkward to use this in the Schrödinger equation. How did people deal with that difficulty? What they did was to change the Schrödinger equation by another equation in which they take the square of this operator, d by dt, on the left, and they put the square of h on the right. You then get the equation h squared d2 by dt squared minus m squared c squared minus h squared d2 by dx1 squared plus d2 by dx2 squared plus d2 by dx3 squared. All this applied to psi equals naught. This is just the de Broglie equation, an equation which was discovered actually by de Broglie before the quantum mechanics of Schrödinger and Heisenberg. And this equation one can easily extend to apply to the case of an electron moving in an electromagnetic field. Well, people used this equation which is a nice relativistic equation. It treats the time on the same footing as the three space coordinates, x1, x2, x3. It doesn't have any awkward square root. It's quite a pleasant equation to work with. But of course, it is not the same as the Schrödinger equation, which has only d by dt. It's got d2 by dt squared instead. Now, if you take the wave function connected with this equation, you can get an interpretation for it by setting up the expression psi bar psi by dx mu minus psi bar by dx mu. Mu here takes on the values 0, 1, 2, 3, so that we have the relativistic formulation required by the Einstein special relativity. We can interpret this as a density in the case of mu equals 0, and a current in the case of mu equals 1, 2, and 3, and we get conservation. People used this expression, the mu equals 0, as the density to replace the mod psi squared of the Schrödinger theory. That was quite all right from the point of view of relativity, but it was not satisfactory for one reason, namely, we cannot call this probability when mu is equal to 0, because it is not positive definite. A probability always has to be positive, otherwise it is just nonsense. Mod psi squared always is positive, while this can be positive or negative. But still, people didn't bother about that very much. They said that perhaps we could call it charge density instead of probability density. However, with that sort of formalism, you have departed from the great power and generality of the original Heisenberg-Schrödinger theory. You can no longer make the sort of transformations from one kind of variables to another which were possible with the original Schrödinger and Heisenberg theory. Well, that was the situation which we had in 1927, and it worried me very much. But it did not seem to worry other physicists at the time. I remember very much an incident at the Solvay conference in 1927. During the interval before one of the lectures, Niels Bohr came up to me and asked me, "What are you working on now?" I told him I was trying to get a satisfactory relativistic theory of the electron. Then Bohr answered, "But Klein has already solved that problem." Klein had this equation and this interpretation. Klein and Gordon had worked it out independently. And Bohr considered that as a solution of the problem of getting a relativistic theory of the electron. I started to explain to Bohr that I wasn't satisfied with that, and wanted to explain to him why, but just then the next lecture started and our talk was cut short, and I never did get a chance to explain just what my objections were to this theory of Klein. The objection, of course, is that we have a very beautiful and powerful quantum mechanics based on this equation of Schrödinger and the corresponding equation of the Heisenberg theory. It is so beautiful, so powerful, that it seemed to me that it had to be right. I was very much impressed by the power of this theory because I had seen it grow up step by step and had taken a part in it. And then people wanted to scrap all this beauty and power and replace this basic Schrödinger equation by something different, something to which you cannot apply the standard rules of quantum mechanics. And that I found just intolerable. I was very much working alone then. The other physicists were pretty well satisfied to go on with this kind of theory here, bring in the spin of the electron and develop their theory. But I just stuck to the fundamental ideas that we did not have a satisfactory relativistic theory of the electron, and it was necessary to make some radical change. Well, eventually I was able to guess what this change has to be. We have in the Schrödinger equation an equation linear in the operator d by dt, and if we are to keep essentially symmetry between t and the three space coordinates x1, x2, x3, we must have an equation that is linear also in d by dx1, d by dx2, d by dx3. We must do something to linearize this square root here. Now, just playing about with the mathematics, playing about is strictly the correct word to use. I was just studying the equations without any very definite object in view. I noticed that if one takes the three variables, sigma 1, sigma 2, sigma 3, which were introduced by Pauli to describe the spin of the electron. The electron has two independent states of spin, and for describing them, we need such matrices as these, containing two rows and columns referring to the two states of spin. If you form sigma 1 P1 plus sigma 2 P2 plus sigma 3 P3 and square it, you get P1 squared plus P2 squared plus P3 squared. So if you're dealing with the square root of P1 squared plus P2 squared plus P3 squared, you can replace it by sigma 1 P1 plus sigma 2 P2 plus sigma 3 P3. There you had a way of linearizing something which was the sum of three squares. Here we need to linearize something which is a sum of four squares. Well, that turned out to be quite a serious stumbling block. We could only do it for three, but it needed several weeks of puzzling over that before I noticed that there was no need to stick to these operators, to these sigma operators, expressible in terms of matrices with two rows and columns. It was quite permissible to go over to matrices with four rows and columns. And then you could linearize the sum of four squares. Actually, you could linearize the sum of five squares, but that was not necessary. Well, that led to a new wave equation. IH d psi by dt minus alpha 1, P1 minus alpha 2, P2 minus alpha 3, P3 minus alpha n MC. This is psi equal naught. There should be another C there. The alphas are matrices with 4 rows and columns satisfying similar algebraic properties to the Pauli sigma matrices. This is such that if you square this, you get some of the squares of these quantities here. These terms here form a way of linearizing this square root. Well, in that way, I was led to think of a new type of wave equation which satisfies the basic requirement of the Schrödinger theory that it is linear in d by dt, and thus it enables you to apply the general transformation theory of quantum mechanics, and also it enables you to apply the standard interpretation of the wave function. Mod psi squared is a probability. You get out for the probability something which has to be positive. Examining the properties of these equations, one found that one could easily generalize it to bring in an electromagnetic field, and one found that the electron satisfying this equation automatically has a spin of a half a quantum, and also automatically has a magnetic moment in agreement with the observed magnetic moment. Well, these were very surprising results and very happy results to obtain. I started out this work without any intention at all of bringing in the spin of the electron. It seemed to me that one, first of all, had to get the satisfactory relativistic theory of a particle without spin, and only after one had solved the problem without spin would it be possible to bring in the spin later on. And here was the surprising result, that the particle with a spin turned out to be really more simple, more primitive than the particle without a spin. And the spin that one was led to in this way was just what was needed to account for the observed spin and magnetic moment of the electron. This equation was applied to the spectrum of hydrogen, and the results were found to be in agreement with observation. Well, there, everything was very satisfactory up to a certain point. But a new difficulty now appeared, namely, this equation allows negative values for the energy. The energy corresponds to the operator IH d by dt, and it can have negative values just as much as positive values, because this expression here is quite symmetrical between positive and negative values with regard to the values that it can take on. This negative energy difficulty appeared at this stage, but of course it wasn't really a new difficulty. It had been present in the theory all along, as soon as one used Einstein's expression for the kinetic energy of a particle. Einstein's expression for the kinetic energy involves a square root. Mathematically, a square root can have negative values just as well as positive ones. the negative energy values for the energy would appear also in classical mechanics. But of course, they never bothered one in classical mechanics because there was quite a big barrier of discontinuity between the positive energy values for a particle and the negative energy values. If you start off a particle in a state of positive energy, classically it always has to remain in a state of positive energy, and you can forget all about the negative energies. In quantum mechanics, the situation is different. In quantum mechanics, a dynamical variable like the energy can make a discontinuous jump from one value to another. We may start off our electron in a positive energy state, apply the Schrödinger equation to it, and calculate the energy at a later time. And then for an electron which is being disturbed by an electromagnetic field, there is a possibility that it will jump to a negative energy state. We can no longer just shut our eyes to the negative energy states. Well, the negative energy states were present, as I said, all along. They were also present in this theory of Klein and Gordon. But people hadn't previously bothered about these negative energy states because there were more serious difficulties. The more serious difficulties were now removed by the use of this equation, and it was only the negative energy difficulty which survived. One frequently notices in developing a physical theory that one removes certain difficulties only to find a new difficulty looming up. And one might at first sight think that one hasn't made any progress. But actually one has made progress because the new difficulty is more remote than the earlier ones. And taking the standpoint of the newer theory, one is better able to study the new difficulty and see how to remove it. The negative energy states which come from certain solutions of this equation are, of course, connected with the matrices having 4 rows and columns. The 4 rows and columns mean a 4-fold increase in the number of states. We need a 2-fold increase in the number of states because each state has 2 spin possibilities. But there is a further doubling. This further doubling corresponds to the theory bringing in the negative energy states as well as the positive energy states. Now we have a theory which predicts the possibility of an electron jumping into a state of negative energy. Electrons are never observed in states of negative energy. A state of negative energy would be something very strange physically. It would mean that the faster the particle moves, the less energy it has. Something completely foreign to all our experience of physical particles in practice. So, one's first attempt to deal with this difficulty was to find some way of excluding the transitions from positive energy states to negative energy states. Schrödinger looked at the problem from that point of view, and he noticed that one can make a small change in this equation as modified by the presence of an electromagnetic field, such that with this small change there are no longer transitions from positive energy states to negative energy states. However, this change spoils all the beauty of the theory. It spoils the relativistic character of the equations. although the effect of the change is quite negligible in the spectrum of hydrogen, still such a change is not acceptable theoretically. It turned out that it just wasn't possible to exclude these transitions from positive to negative energy states. The only way one could deal with the situation then was to find a physical meaning for the negative energy states. If one looks at the wave function corresponding to a negative energy state, one may construct a wave packet and see how it moves in a particular electromagnetic field. One sees that it moves as though it had an opposite charge to the ordinary charge on the electron. The ordinary charge on the electron is a negative charge, so the negative energy state would move as though it had a positive charge. That suggests that one should try to connect it with a particle with a positive charge, but still we cannot make that connection directly, because although particles are observed with positive charges, such particles certainly do not have negative energies. In order to get a proper understanding of these negative energy states, one has to bring in a new property of electrons, the property that two electrons cannot be in the same state. This is known as Pauli's exclusion principle, and it forms the basis for the whole theory of the chemical structure of the elements. If we take any particular element, we have the positive nucleus in the center, various electrons moving around in certain states, and the electrons will try to crowd into the states of lowest energy. But there is this exclusion principle which tells us that there cannot be more than one electron in any state, so that all the states of lowest energy get occupied in a normal atom, and the higher states are unoccupied. Now this connects up with the chemical theory of the valency of atoms. The chemists know that there are certain atoms which are inert, the rare gases, and these atoms are explained as having all the electrons filling up closed shells. Now there are some atoms with one or two electrons outside closed shells. These are the alkali elements or the alkaline earths. These outside electrons each provide valency 1 for the atom. Now there's also a possibility of having one of the closed shells not complete. There might be a hole in it, and such a hole also counts as chemical valency 1. That applies to the halogens and to the oxygen-sulfur group. We have, to some extent, a symmetry between the holes and the external electrons. Now, I knew about this theory of valencies quite well, and it occurred to me that one could treat the negative energy states in a corresponding way. One could suppose that what physicists ordinarily mean by a vacuum is not a region of space where there aren't any electrons. It would be a region of space where all the negative energy states for electrons are occupied. That, in fact, is the most reasonable definition for a vacuum, because you might consider the vacuum to be the state of lowest energy, and putting electrons into negative energy states, you get a negative energy each time you do it. So the state of lowest energy would have all the negative energy states occupied. we get a new picture of the vacuum. Rather disturbing to begin with, but still one can accept it. The vacuum is a sort of sea of negative energy electrons. And then we may have departures from the vacuum in two ways. We may have some electrons lying outside in positive energy states. These would be the ordinary electrons, and they cannot then normally jump into negative energy states because the negative energy states are occupied. However, there might be a hole among the negative energy states, just like a hole in the closed shells of chemical elements. Such a hole will be a region of positive energy because there is a lack of negative energy there. And also, it will behave like a positive charge. So that the hole will appear as a reasonable physical particle with a positive energy and also a positive charge. There one had a picture which gets over the main difficulty about electrons jumping into negative energy states. An electron cannot jump into a negative energy state unless there happens to be a hole there. And in that case, the electron and the hole just annihilate each other. The things that we can observe will be departures from the vacuum state, namely electrons in positive energy states, and also the holes, which have positive energy and also positive charge. Now, I felt right at the beginning that there ought to be symmetry between the holes and the original electrons, but that was a serious difficulty because at that time the only positively charged particles known were the protons. So it seemed to me that there must be some factor which will disturb the symmetry, which results in the holes becoming protons. And when I first put forward this idea, I called it a theory of electrons and protons. In order to understand why I did this, which seems rather stupid nowadays, you must remember that at that time people were very unwilling to postulate new particles. There were just two kinds of electricity known, negative electricity and positive electricity. There were just two kinds of particles known, electrons and positrons. And it seemed that the two kinds of particles must correspond to the two kinds of electricity. And therefore, I just didn't have the courage to propose that we really had a new particle there. However, the mathematicians worked on these ideas and very soon showed up that the holes would have to be symmetrical with the electrons and would have to have the same mass as the electrons. I believe Weil was the first to point it out categorically. These holes must have the same energy as the electron, the same mass as the electron. The question then arose, why is it that experimenters had never observed particles with the same mass as the electron and having a positive charge? Of course, the answer to that question was simply that they hadn't looked in the right place. People had made studies of the motion of particles in the Wilson chamber, which shows up the track of a particle, and if there's a magnetic field present, the track is curved. Now you see a curved track in one of these Wilson photographs, but just from looking at this track, you cannot tell whether you have an electron moving like this or a positively charged particle moving like this. They would both make the same kind of a track. Now, people had observed that when they have radioactive sources, there often seem to be an electron moving back into the source. That's how people interpreted those tracks, which were really positively charged particles coming out from the source. Everyone in those days was unwilling to postulate a new kind of particle. There are even some published pictures of which were described as electrons moving into the source. Of course, with this theory of mine, there was a possibility that we had really positively charged particles. And Blackett, who was working in Cambridge with me, soon obtained evidence from cosmic ray showers that there were particles, the ordinary electrons, which are curved in a magnetic field, corresponding to their negative charge, and other particles with the same mass curved in the opposite direction, corresponding to their positive charge. Blackett was a bit cautious in publishing his evidence, and the experimental discovery of the proton, of the positively charged electron, was really obtained by Anderson. Anderson obtained one picture of a track of a particle moving through a plate. So that's plate like this. That makes it quite definite in which direction the particle is moving. It must be moving like this, suffering an energy loss here. It cannot have been moving in the reverse direction, suffering an energy gain. Well, this one photograph of Anderson was quite definite to establish that he had there the positively charged electron, or the positron as it was named. And it had the same mass as the electron. Well, that completes the story of how the positron was discovered. Anderson, I heard, was working quite independently of my theory and was not influenced at all by it, simply studying the pictures which he could obtain with a Wilson chamber in the magnetic field. In that way, the new particle was set up. Just previously to that, another new particle had been discovered by Chadwick, the neutron. And since those days, 1932, 1933, very many new particles have been discovered, and people nowadays are only too willing to postulate new particles on the slightest evidence, either theoretical or experimental. A very different climate of opinion from what one had before 1932. This new particle, the positron, has many interesting properties. It can annihilate with an electron. An ordinary electron can jump into the hole, fill up the hole, and then the electron and the positron have both disappeared. Their energy has gone off into some other form. It may go off into the form of two photons. If the electron and the positron both have the same spin, then it turns out that they cannot annihilate each other with the production of only two photons. They have to produce at least three photons. That gives rise to the possibility of an electron and a positron close together, circling one another, like the electron and the proton in the hydrogen atom, and they are fairly stable when the spins are parallel, because the direct two-photon annihilation is no longer possible. There's only the more indirect three-photon annihilation. We get a new sort of atom just with a positron and an electron. It has rather a short lifetime, somewhere around 10 to the minus 8 of a second, but still one can observe its spectrum, and it is quite an interesting thing to play with experimentally. The theory has been confirmed by experiment all along everywhere. And we have there the beginning of the idea of antimatter, this idea that for particles there exist antiparticles can be applied for any kind of particles which satisfy the exclusion principle of Pauli, such as protons, neutrons, and so on. Antiprotons, antineutrons have been discovered. Well, that is really the end of the story of the positron, but I would like to say that I believe this story has a moral for present-day theoretical physics. Present-day theoretical physics is not in a satisfactory state. We have this theory for a single electron moving in an electromagnetic field. Now we want to generalize this to several electrons, and we want to take into account correctly the reaction of the electron on the field. That means we want to build up a general quantum electrodynamics. Now we have the principles of quantum mechanics, those general methods where we can have absorption and emission operators and bring them into the Hamiltonian. We can set up a Hamiltonian describing the particles interacting with the electromagnetic field. And then a new phenomenon arises which one might not have expected to begin with, a phenomenon which is called renormalization. We start off our equations involving a parameter m for the mass of the electron, a parameter e for the charge of the electron, and then developing the equations, we see that the observed mass is not the same as the mass that we started with. It's something different from m. That is to be interpreted as the electron acquiring an extra mass from its interaction with the electromagnetic field. Similarly, the charge on the electron, which we observe, is not the same as the original charge, and the discrepancy can be assigned to the electron polarizing the vacuum around it, and in that way attaching sort of a cloud of electricity to it, which results in the observed charge being different from the original charge appearing in the equations. Now, this is all quite sensible and reasonable, but there is the difficulty that when we proceed to solve the equations, we find that these renormalization factors are infinitely great. If they were small factors, or even if they are finite factors, we could say that we understand the theory, but they turn out to be infinitely great. Now, what does that mean? Most physicists at the present day say that that doesn't matter. We can set up rules for discarding these infinities. Turn a blind eye to the infinities. make the rules precise so that after they are discarded, there are some definite finite terms left. And these finite terms which are left turn out to be in very good agreement with observation. One finds very small corrections in the spectrum of hydrogen, known as the Lamb shift, which when one calculates by this method, cutting out artificially the infinities, are in very good agreement with the experimentally observed shifts in the spectrum of hydrogen. This Lamb shift provides a beautiful confirmation of these rules for discarding the infinities, and most physicists are very happy with this situation, and they say that the problem of quantum electrodynamics is essentially solved. Well, I feel very unhappy about it. I think that this sort of theory is just as bad as the Klein-Gordon theory. Mathematics doesn't allow you to discard infinities just when they don't suit you. If they are present in the equations, it means there's something wrong with the equations. So I feel that it is imperative to modify the basic equations of the interaction of electrons with the electromagnetic field in some way so that these infinities are removed. I think I'm pretty well alone among physicists in that way. But I was alone also in 1927, and it turned out to be the right thing. So I'm always hoping that some way will be discovered of modifying the basic equations for the interaction of electrons with the electromagnetic field in such a way that these infinities never occur. The presence of these infinities means that there is something wrong with the theory, and one must not be complacent and just go on making further and further developments of this theory, which is basically wrong. Thank you.
This applause shows you the admiration for your masterful lecture, with which you have shown us the strange and mysterious ways you have followed for finding your discovery, and you have also pointed out the present implication and also for the future of physics. Thank you very much.
Thank you.
If anybody wishes to make any...
I would like to make a little comment, and that is that I'm happy about your unhappiness about the present state of electrodynamics. And I want to quote Pauli, who called this renormalization physics Resignationsphysik.
Yes.
So physics of resignation, because, I mean, you cannot explain the mass of the electron, you can't explain 137, so you put it into the equations and chuck out everything, I mean, that doesn't agree with these numbers. And of course, this is not the method in which science should be made, and you should try and find out, I mean, the basic problem of explaining 1 upon 137, and in some way, through a universal constant, the masses of the particles. Where is this universal constant? One doesn't know. I mean, maybe Fermi's constant or something like this. But as I said, I repeat now, I'm happy about your unhappiness about the theory. Thank you.
Thank you. Could I make one further remark?
Yes.
I think the future development will come by people first of all finding the equations. and then later on finding the physics. My own work is concentrating on finding equations. I think that that is the only method in which this sort of problem will get solved.